Hello National 5, it's Mr. Neil here. In this video we're going to focus on analysis, design, testing and evaluation. So the parts that we're going to cover in this video from the SQA course specification are here. We're going to talk about functional requirements with analysis. We are going to talk about the design notations of structured diagrams, flowcharts and pseudocode. We're going to look at different test data, so normal, extreme and exceptional. We will look at how we identify syntax, execution and logic errors, and then we'll evaluate our program to make sure that it's fit for purpose, efficient, robust and readable. What we're really going through here is the development cycle for software. This is called an iterative model, or sometimes called the waterfall model. So we start at analysis. After we've analysed a problem, we go and design a solution. Once we've designed the solution, we then implement the solution. Once we've implemented it, we test it. Once we've tested it, we then document it. And once we've documented it, we evaluate it. But at any point through this cycle, if there is a problem or something we can't fix, we can iterate back round and have a look at it. This normally happens when you test the program, find something wrong with it, you've then got to iterate back to implementation. So let's dive in and have a look at analysis. So with analysis, we need to be able to identify the functional requirements of a program. Before we look at the functional requirements, we need to think, what is it that we actually want our program to do? And that's referred to as the purpose of the software. And this works out what it's supposed to do and how complex the overall project will be. So it's a clear description of what the program is required to do, and it should really explain the main points in a really straightforward way. If we have a look at an example here, the operators of Edinburgh Castle would like a program developed that will allow their staff to enter the number of tickets sold each day. The program should then calculate the output, the total number of visitors in a year, and the average number of visitors per day, week and month. So we can see there really clearly this purpose states what this program should do. And from this purpose statement, we can identify the functional requirements of our program. And the functional requirements are the inputs, so what information will we be inputting into our program? What processes is the program then doing with that inputted data or stored data? And then the outputs. What is that program then outputting back to the user to see? So if we keep the example of Edinburgh Castle, okay, our inputs are going to be the number of days we're open for and the number of tickets each day. Once we've got this information, we're able to calculate the total number of tickets. As well as that, we can then calculate the average per day, per week and per month. Once we've done all these calculations, we're then going to pass that information back out to the user. So you can see here, we're taking the purpose statement and splitting the purpose statement into what we need to input into the program, what the program does with our inputs, and then what it outputs back to the user. So within analysis, we're identifying the functional requirements, which essentially are our inputs, processes, and outputs. Now it's on to design. Within design, we are taking our analysis and we're designing a solution to make sure our functional requirements are met. And we might use this using a pseudocode, using a flowchart or structured diagram. So at National 5, we need to be able to read and understand all three, but you're only expected to be able to write one of them. So we're going to have a look at all three of these in this section. Let's dive in and start with structured diagram. So a structured diagram is a graphical notation, and it's a way of taking the overall problem and breaking it down into sub-steps. And we keep breaking down these sub-steps until they're in their simplest forms. And down the right-hand side here, you can see all the different graphics that we will use. So a square box is a process, an oval is a loop, selection is in a hexagon, then a predefined function is in a box with two lines down the side. So let's have a look at an example of a structured diagram. So here we have got our big problem. We want to calculate the average score for a class. So how are we going to do that? Well, the first thing is we need to repeat 20 times. And what is it that we're going to repeat 20 times? Well, we're going to repeat the get score from the user and add that score to a total. So we're going to do this step here 20 times. Once we've done that step, we're going to move on to divide the total. Once we've done that, we're going to move on to display the answer. How are we going to do that? Well, we're going to round the answer to 0 decimal place and then show the answer on the screen. So with a structured diagram, we've taken the big problem and broken it down into its smaller parts. Moving on now to flowcharts. So flowcharts is another graphical design notation, but this time it shows the flow of the program. It shows how we start at the start of the program, flow all through it until we get to an end point. So with a flowchart, there is always one start point and always one end point. You'll notice that we've got a similar set of symbols to a structured diagram. There are some differences. The common ones that we'll use a terminal, so this shows the start and the end. We'll use a parallelogram for inputs and outputs. We'll use a diamond for decisions, a rectangle for processes, our lines for a predefined function. You'll notice in this stage that there is no symbol for a loop. So we need to use a combination of decisions and flow lines to show the loop. Let's have a look at the same program we looked at for a structured diagram. We want to calculate and display the average for a class test. So we're setting the score, the total and pupil to values. So this is us declaring variables. We're then getting a score from the keyboard. We're adding that score to the total. Then we're asking, does the value pupil equal 20? And if it's not, we're branching off, we're adding 1 to pupil, and we're going back round. So this here is our loop. Once pupil equals 20, we're going to go down the yes bracket, and we get to this wee circle here. This is called a connector, and what that means is it's going to connect to the code up here. We go through set the average to total divided by 20, round it, so this is a predefined function, and then display it to the user. With a flowchart, there is a single flow through it, and where we have a decision, we always have a yes branch and a no branch. Pseudocode isn't graphical, it's text, it's English phrases that are used to describe the processes being carried out. Now, there is no specific standard for pseudocode. When you go into industry, companies and businesses might have their house style and method of doing it, but for our purposes, there is no specified way of doing it. Steps in pseudocode are often numbered. We can then refine that step, making it simpler and simpler and simpler, to the point and stage where one line of pseudocode represents one line of code that we will then implement in our chosen programming language. So here we have our program again. We're looking to calculate and display the average for a class test. Our main steps are getting the scores times 20, calculating the average and displaying the average. So to get our scores, we're going to set the total to 0. We're going to start a loop that goes from 1 to 20. We're going to get the score from the user. We're going to add that score to total and keep it in total, and we're going to loop round. Step 3, display the average. How are we going to do that? Well, we're going to round the average to 0 decimal places and then display the average. And I hope you can see here with these refinements how you would translate each of these individual lines to one line within a programming language. Once you've built the program, you then need to test it. And in the process of testing it, you will identify syntax, execution and logic errors, and you will use normal, exceptional and extreme data to help you do your testing. So let's have a look at the errors first. So when we're programming, errors can be categorized into 3 different types: syntax, execution and logic. So let's start with syntax errors. Syntax errors occur when you break the programming language. So you make a mistake within the way that you're writing the programming language. So for example, here in this Python code, I have missed the colon at the end of my if statement. I have then gone and tried to run my program, and my development environment has just stopped. It's not even run the program, and it's telling me there is a syntax error. So with syntax errors, you're unlikely to be able to run the program, and it's because you've broken a rule of the programming language. Execution errors occur when the program is running, and these will cause the program to stop abnormally. So here we've got two examples of an execution error. The first one is dividing by 0. Dividing by 0 is a mathematical impossibility. So when it gets to this line here, average equals total divided by 0, it'll just crash. Your program will stop working and it will have no idea what it's doing. Likewise, if I've got two strings, so I've got the string Catherine and the string Janeway, and I try and times them together, well, you can't times text. So that is an execution error. Your program will get to that line there and just stop working. The third kind of error we can get is a logic error. And logic errors is where there's a problem with the way the program works. So your code is perfectly fine, there's no syntax errors, there's no execution errors. When you run the program will work, but it doesn't give you the expected result. Let's have a look at the example on the left. We are adding three numbers up, 36, 32, 42 and 47. And we then want to find the average of those four numbers, but we're dividing by 3, not 4. So that means the program will work, we just won't get the average that we expected. Let's look at example on the right. We're getting the temperature of water from the keyboard, and we have to determine whether it's a gas, liquid or solid. So let's assume I take the temperature 100. So if 100 is greater than 100, well, that's not the case. Else if 100 greater than 0, well, it's greater than 0, and 100 less than 100, well, it's not less than 100, then else display solid. So if I enter 100, I'm going to get solid. But we know at 100 degrees, water is a gas. So that, in this case, our problem has a logic error. It works, but we don't get the result we expect. So with logic errors, we have to test our program to make sure it's working. So how do we test? Well, before we even consider running our program, we identify different kinds of data that we can use to test our program. So there are three different kinds of data. There's normal, extreme and exceptional. So normal is data that you'd expect your program to accept and you'd expect that it would work. Extreme is data at the ends of what is acceptable. And exceptional is data that your program should not work with. So if we take an example here, consider a program that will check if a dice roll is valid. So we're working on the assumption here that a dice can have a number between 1 and 6. An example of normal test data would be 2, and we'd expect that to be a valid number for a dice. 4 would be a valid number. Extreme is at the end of what is acceptable. So the lowest number I can throw is a 1, and the highest number I can throw is a 6. Exceptional is data that we don't think our program is going to work with. -2 is going to be not valid. 141 is not going to be valid. 2 is going to be not valid. Now that I've identified my data and I've written what I expect my program to show, I can then go to my program and enter those numbers. So if I enter if greater than or equal to 1 and less than 6, well, the number I've entered is 2, so that is valid. I've entered 4, that is going to be valid. 1 is valid because it is greater than 1 and less than 6. 6 is not valid because while it is greater than or equal to 1, it is not less than 6. So in this case here, my actual result doesn't match my expected result, so I need to go back to my code and then change it. Exceptional -2 doesn't match that criteria, so we're going to get not valid. 141, not valid. In our case, if I was to type in 2, I would get an error. And that's because my program's not expecting text, expecting numbers, and that would cause an execution error. Once you've tested a program, it's essentially finished, but we're going to evaluate it. And we're going to evaluate to make sure it does what we want it to do, it does it efficiently, it's robust, and the code itself is readable. So fit for purpose is making sure that the program matches the agreed criteria during the analysis stage. So you're looking at your purpose statement, you're looking at your functional requirements and going, does my program do what I want it to do? Efficiency is all about making sure the code within your program is efficient as it can be. So how quick is it to write, understand and update your code? Does it run it with the minimum number of instructions, and is it easy on the amount of memory that it uses? So things that we can do to make our program more efficient is we can use repetition. We can use array instead of variables. We can use select statements such as else if or else as opposed to multiple if statements. And we can use the logical operators and or to reduce the complexity of our selection statements. So let's have a look at an example of what I mean. On the left here, we have got a program that is taking in 5 numbers, adding them up, and finding an average. We know through our standard algorithms, we have one called running total inside a loop, so we can implement that. Here, I've got different numbers, so instead of storing those in variables, let's use an array. Robustness refers to your program's ability to handle errors. So if we were looking at real-world examples, we might need to rely on a file, whether it inputs a file or outputs it. So what happens when the file's not there? What happens when I'm trying to print a Word document and the printer's not connected? What happens if I'm looking for marks between 0 and 100 and the user inputs 123? So robust programs should always cope with unexpected errors and give useful feedback on that. So the purposes of National 5, we've got input validation to help with robustness. And lastly, readability. So we're thinking about the actual code itself that we as developers see. So we can add meaningful variable names to our code, we can make use of white space, we can have indentation, and we can have internal commentary. Looking at the example on the right here, there is none of that. And it means that the code is slightly more difficult to read. If we look at the example here on the right, we have added all of those. So we have got internal commentary, and that explains to the developers what this code is doing. We have got meaningful variable names, so we know in this case what A is number and B is guesses. We have got white space separating it all out, so it's really clear to use. And we've got indentation, so I'm repeating and this is happening in the repeat. Here's my if, this is happening in my if statement. So in this video I've covered parts of analysis, design, testing and evaluation. And that means you should be able to do all of these things here.